Hello, welcome to the fourth CJP video podcast dealing with landing performance. Today we're going to talk about some variations in runway surface and how that can affect our expected performance when we're landing on a non-dry runway. We looked a little bit at the last time at the difference between a grooved and non-grooved runway, and we're going to look a little bit more into how differences in the surface can affect the expected stopping ability. So runway surfaces, looking at a couple of somewhat recent accidents that were runway overruns. These occurred at two different airports, but they have something interesting in common that we think is worth being aware of as you perform your planning for a landing on a non-dry runway. In one event, the aircraft was landing in a situation of heavy rain, 2 miles visibility. In the other event, the aircraft was landing in moderate rain, also with 2 miles reported visibility. Both cases, the winds were either calm or fairly light. And they both had something interesting in common. Both runway surfaces were 5,000 feet or more. In one case, 5,000 feet of available landing distance. In the second case, 6,000 feet of available landing distance due to a large displaced threshold. But they both were concrete surface runways. In some parts of the country, landing on a concrete runway is fairly uncommon, and we're used to landing on asphalt runways. But in certain parts of the country, concrete runways are much more prevalent. NASA has done some studies. Unfortunately, these are fairly dated to the roughly late 60s, early 70s period, are the most recent we've been able to find. But they've done some studies where they looked at different types of runway surfaces and the effect that the runway surface has on the friction landing on that surface when the runway is wet. So all of these lines on the screen right now represent a different type of asphalt or different type of concrete that was in use at the time the study was done. Again, this chart, we looked at a similar one last week, starting on the right side of the horizontal axis. We start with about a 90 knot ground speed, so equating to a aircraft touching down at maybe around 100 knots with a 10 knot headwind. And then as it moves left, the line is showing in all cases except for one, an increase in braking effectiveness as the ground speed decreases. At the top of the vertical axis is 100% of dry runway friction. So that would be what we would see on a dry runway. And so you'll see some of these surfaces provide for, in the best case, 85 to over 95% of dry friction, whereas some of these surfaces provide for as little as 10% and never better than 35% of runway surfaces. So the first takeaway from this chart is, as we discussed last week, when we are landing on a non-dry runway, we cannot expect a repeatable, scientifically determined amount of runway use each time. Every landing is going to be different. The variables between the runway surface, as we see here, make a tremendous difference. So we might land on an asphalt runway on Monday when it's wet. We might land on a different airport's asphalt runway on Tuesday, and because the construction differs in that runway, we might experience a very different amount of braking, even though the reported rainfall, for example, was the same. So this, again, is why it's so important that we factor our landing distances and apply that safety margin, especially when we are talking about non-dry situations. Now, what's interesting, if we cover all of the asphalt runways with the yellow line, and we cover all of the concrete runways with the red line, we do see a trend emerges, which is that by and large, asphalt runways tend to achieve higher friction than concrete runways, with one exception in the middle of the chart. But as a rule, we expect that the asphalt runway is going to have a greater percentage of dry runway effective friction. NASA did a similar study with a different aircraft. The previous example were transport category jets. This was with a transport category turboprop. And this is worth looking at again because it emphasizes how different the expected braking performance can be once we start talking about different runway surfaces. So there's a lot of information on this chart. Just to give you a quick overview of what we're looking at. For each type of runway surface, there is a grooved and ungrooved landing distance information displayed. Okay, so the ungrooved is unshaded, the grooved is shaded. So starting at the top, we see that as expected for a dry runway, the amount of runway required for the aircraft to stop was the same if it was grooved or ungrooved. As we would expect, it really makes no difference when we're talking about a dry runway. Then we have two types of concrete runway. We have two types of asphalt runway. And then at the bottom, we have a contaminated concrete runway, and we have then a slush-covered concrete runway. What I really want to focus on here, though, are the second, third, and fifth lines. The second through the fifth, the two wet concrete and the two wet asphalt. These show us that, first of all, when we are landing on a grooved runway, we do see very little variation from the dry runway when we're landing wet. So this is good news. On a grooved runway, unless we're getting into standing contaminated water, second from the bottom, we would expect that with non-contamination, we would expect that the stopping performance would be fairly close to the dry performance. However, we see that when we're landing on an ungrooved runway, we start to see a pretty big difference in stopping performance depending on the type, the construction of the runway. So the two asphalt runways are just two different types of construction. Aggregate size, one is a little smaller than the other. The two types of concrete runways are two different construction methods as well. The A and B is not a runway surface that we're likely to land on. That is a concrete runway with absolutely no texturing applied. So that's not something we're realistically likely to see. But C and D are for a textured concrete runway. That is still a method of construction that is allowed under the guidance to airports that the FAA publishes. So the runway type we see on C and D for a concrete runway is very representative of what we might see. And it's interesting to note that in the case of an asphalt runway that's not grooved, in this particular aircraft, we saw an increase of roughly 1,000 feet of landing distance necessary. Whereas when we look at case C and D, we see a 1,500 foot increase. And we see that we can expect roughly 2.5 times the dry stopping distance necessary to stop an aircraft, again, taking out the air distance, when we're landing on a ungrooved concrete runway, even a textured one. The study was also done with an F4, which is interesting for some light jets that do not have any type of spoilers, because the F4 likewise does not have any speed brakes or ground spoilers. In this case, it simply exaggerated the differences, and we see on a ungrooved runway even larger percentage increases. So the particular accident that we looked at, this was a Phenom 100. The aircraft landed, and the captain applied the brakes and sensed absolutely no braking effectiveness. The NTSB later released the information from the flight data recorder, and the maximum deceleration was only slightly over 1/10 of a G. So very little deceleration would have been experienced by the pilots. So little deceleration was experienced that the pilot thought perhaps they had a brake system failure. So the crew reverted to the emergency brake. In this aircraft, as in our citations, the emergency brake does not have any type of anti-skid functionality. So therefore, on a wet or contaminated runway, we would expect when using the emergency brake that the braking effectiveness will decrease. So utilizing the emergency brake, the aircraft was not able to stop on the runway and continued past the end of the runway into a grassy area and a ditch. If we run the performance for the conditions that existed, we see that on a dry runway, this particular aircraft we would have expected to require a little bit over 2,700 feet of stopping distance. The NTSB and the manufacturer recreated the performance that existed at the time. Using the deceleration that was measured, they were able to calculate the friction that existed, and they determined that had the emergency brake not been set, had the normal braking just been applied, the anti-skid allowed to do its job, then the aircraft would have stopped about 800 feet from the runway threshold. This is a 6,000 foot landing distance available, slightly over 6,000 feet. So this means the aircraft would have needed 5,200 feet to stop. And from our charts we saw before, we expect roughly 2.5 times the dry stopping distance, taking out our 1,000 foot of air distance. If we multiply that 1732 by 2.5, add the 1,000 feet back in, we come pretty close to that number. We determined, just using a real simple 2.5 rule of thumb, that the aircraft would have needed 5,300 feet. Again, the NTSB calculated they would have needed between 52 and 5,300 feet. So that rule of thumb works fairly well in this situation. So important takeaways from here. One, we do see if we're landing on an ungrooved runway, the type of runway surface starts to become very important. And when we are landing on a concrete ungrooved runway, there is historical evidence and empirical evidence that suggests we should use extra caution and be biased towards using our contaminated runway numbers, not our wet runway numbers. Second takeaway here is that there have been many accidents where pilots have landed on a contaminated runway, and because the braking is so low and feels as if the brakes are not working, they revert to the emergency brake without any display of an actual anti-skid failure. This has historically been shown over and over to lead to runway overruns, sometimes blowing tires. So there's a good lesson in that as well, that if we are landing on a wet runway, we should be expecting that when we start braking, we will not feel a high level of braking effectiveness. And we should not be thinking of reverting to the emergency brake unless we are presented with a CAS message or annunciator as appropriate that tells us that we have a system failure. A survey from Boeing shows that of the runways that were included, I'm not aware of what the cutoff was for runway length, but approximately 1 out of 3 or 4 runways in this survey were concrete runways. And of those concrete runways, almost 90% were ungrooved. So this is something, again, to be aware of and to be mindful of. This information is really only available to us from the chart supplement. We look in a chart supplement, we can see with the runway description what the type of runway surface is, and we can see if the runway is grooved or not. In our Jeppesen 10-9 diagram, we only have some of that information